Good morning and welcome to Tech 240 for Wednesday, October 28th. We're just a couple of days away from Halloween. A couple of due dates coming up, and we have Lab 13 is due today by 11:55 p.m. That's the one on AC motors. We have the DC motor extra credit opportunity where you build your own DC motor and then send me the video of it running. That is due on November 1st. That's the day before the exam. And then we have exam 2. That's going to be next Monday on November 2nd. It'll be set up very similarly to exam 1, and we'll talk more about that in the second part of today's class session. But the very last topic that we've got in this section of the class is about transformers. And transformers are really pretty straightforward after all that we've talked about so far. They're really going to be pretty easy. But first I want to talk about, why do you need transformers? Why do we even need to use transformers? And the answer has to do primarily with our need to transport electrical energy. The way that our electric grid is primarily set up is that we have large generating stations like, say, nuclear power plants or coal or natural gas powered power plants, or wind farms or solar farms, doesn't really matter. But we have large centralized power stations to generate electricity, and then we have to transport that electricity to somewhere where it's going to be consumed, say, in a city or a town or in the countryside or wherever, right? But the point is, it has to be transferred, it has to be transported from point A to point B. And to transport it, we're going to have wires that are going to run from point A to point B. And we know that for a given amount of power consumption, right? So if a town or a city or some location has a required amount of power that they need to fulfill their daily needs, for a given amount of power, power is equal to current times voltage. So you can either increase the voltage and decrease the current, or decrease the voltage and increase the current, or some mixture thereof. For a given amount of power, you can play with what the voltage is and what the current is. All right, so we're going to put the electrical energy on the transmission wire to get it from point A to point B. And for a given amount of power that's being provided, you can increase the voltage on the transmission line, in which case you would reduce the current flow through the transmission line. Or you can reduce the voltage, in which case you would need to increase the current flowing through the transmission line to get the same amount of power. All right, so the power is constant. I can play with the current and the voltage. All right, now there's a better solution. You can play with which you want to increase and which you want to decrease. However, there is a big penalty in efficiency for increasing the current, because the current induces losses in the wire proportional to the current squared. So if you have twice the amount of current flowing through a wire, you have 4 times the amount of losses inside the wire. So that gets to be a pretty big penalty when you're talking about hundreds to thousands of amps going through those big transmission lines. All right, so clearly there is an advantage in efficiency to increasing the voltage on the transmission line and thereby decreasing the current. I will say that there are still losses that you get by increasing the voltage. They're called corona losses. It's kind of beyond the scope of this class, but basically it happens when you get really high voltages. You actually ionize the air around the transmission line, but that only happens at really high voltages. We're talking 500,000 to 1,000,000 volts where it's significant, and they're relatively low compared to the losses that you get from pushing thousands of amps of current through the transmission line. So what I'm trying to convince you of right now is that there is an incentive for us to transmit energy along transmission lines at a high voltage and a low current through the wire. Okay, all right, so that's why we want transformers. However, on the other end, when you're at the city or the town, do you really want 100,000 volts coming into your house? I don't want a wire carrying 100,000 volts or at 100,000 volts in my house, because that's dangerous. you would need to have a ton of insulation built around anything with those wires. So if you had a light switch and the wire had 100,000 volts, your light switch would be this big because it has to have so much insulation around it. So when you're inside a house where you're actually going to use the electricity, you don't want it at a really high voltage. You don't want it at even thousands of volts, much less tens or hundreds of thousands of volts. So there's an incentive for us to increase the voltage at the point of generation so that we can put it on the transmission line, transport it to where it needs to go, and then at the point where it's going to be consumed, reduce the voltage back down to a reasonable amount of voltage that is safe to have in a home. And so that the devices that you use the electricity with don't have to be ridiculously insulated and very expensive. All right, so to talk about the operation of the transformer, I'm going to switch over to the document cam. In order to start to describe the operation of a transformer, we're going to start by making an electromagnet, like we've talked about before. So this is going to be the core of our electromagnet. It's just a cylinder, probably made out of steel. Steel would be a good choice for a core material. And we got to have windings around this core material. So I'm going to draw these windings. I'm going to have an applied voltage here. And I'm going to draw these windings here. Okay, so we're wrapping the blue wire around the core of what is going to be our transformer. And we're going to call this set of windings the primary windings. There's going to be a second set of windings, but right now we've just got one set of windings, and we'll call that the primary. So I'm going to write V sub P, where P stands for the primary, okay? And what I'm interested in here is the magnetic field that's going to be created around the core of this, what's right now an electromagnet, right? So if we apply AC voltage here, then we know that we're going to get a changing magnetic field right here, right? If I apply a positive voltage, like the positive waveform of the AC voltage, I'm going to get a magnetic field in one direction. And then if my AC voltage goes negative in the negative half cycle, then my magnetic field is going to flip and go the opposite way, right? So as my AC voltage goes positive, then go back to zero, then goes negative, then back to zero, then positive and negative, and so on and so forth, my magnetic field around here is going to be pulsating and flipping, right? It's going to be doing this, all right? So I want to make a relationship. I want to write a relationship between the applied voltage and the magnetic field around here. And we already actually have one. We have a relationship between those. We can actually use Faraday's law. So we can say that the voltage that's applied to the primary is equal to negative N, where N is the number of turns wrapped around here, times the change in magnetic flux per unit time. So this is the rate of change of the magnetic flux around this magnetic field. All right, so that'll work. Let's make this more specific. We'll say the number of turns in the primary. So let's have this equation right now be the relationship between the primary voltage that's applied right here, let's say by the generator, and we're going to want to, let's say, increase the voltage to put it on the transmission grid. All right, so let's say for right now, let's say this is the voltage that is applied by the generator, and that has a relationship to the magnetic field around here through this expression right here. It's equal to the negative in the primary, number of turns in the primary, times the changing magnetic flux around here. So this is the rate of change of the magnetic field around this core of this transformer. All right, that's good enough for now, but we're going to do one more thing with this design because it's a transformer, not just an electromagnet. And I'm going to draw a second set of coils around this core, right? A second set of coils. And I was just thinking, I was about to draw this in orange, but blue and orange, that's a bad combination of colors. That's University of Illinois colors. So let's use red. All right, blue and red is better. All right. So I'm going to draw a second set of coils around this electromagnet. It's going to be the core of the transformer. All right, so I'm going to draw it kind of like this. And remember, each of these wires, it's magnet wire, which means it has a thin layer of insulation on the outside of the wire. So there's going to be no electrical conduction between the blue wires and the red wires. All right. First of all, I'm drawing them separated. In real life, they wouldn't be physically separated, but they would not be electrically conducting from one to the other because they have insulation on the outside of the wires. All right. So, yeah, let's call that good. Okay. So this is coming over here. And this, you might guess, is going to be our secondary. These are our secondary windings, and this is going to be the secondary voltage. So we'll abbreviate that V sub S, S for secondary. All right, and once again, I have a relationship between the voltage in the secondary windings and the magnetic field or the magnetic flux, the changing magnetic flux around this core material. And once again, I can write that relationship using Faraday's law. So this time I can say the voltage in the secondary is equal to negative N, where N is the number of turns in the secondary windings, times the rate of change of magnetic flux. All right, so in both cases, in the primary windings and the secondary windings, we have a relationship between the voltage across those windings and the rate of change of magnetic flux around this core material. And it's also related to the number of turns in the windings, right? But what can we say about this change in magnetic flux compared to this change in magnetic flux? Well, what we can actually say is that they're the same. They're the same because they share the same magnetic field. So this term right here and this term right here are the same because they're both wrapped around the same core material. Therefore, they share the same magnetic flux. So now let's make an expression on both sides where we're solving for just the rate of change of magnetic flux. So over here, we're going to solve for this, and over here, we're going to solve for this. All right, so we can do that by dividing both sides of this equation by N sub P. So I have V sub P divided by N sub P equals negative rate of change of magnetic flux per time. And over on the right side, I'm solving for this. And so I'm going to divide both sides by N sub S. So I have V sub S divided by N sub S equals negative rate of change of magnetic flux. And so the same thing applies down here. We said that this is the same as this. Well, this is the same thing, but the negative. So the negative rate of change of magnetic flux per unit time is equal to the same thing over here because it's the same magnetic field. So if this, I'll stick with the same colors. So if this is equal to this, if this is equal to this, and this is equal to that, and this is equal to that, then I can say that that is equal to that. The ratio of primary voltage divided by turns in the primary is equal to the ratio of secondary voltage divided by turns in the secondary. All right, so we can write V sub P divided by N sub P equals V sub S divided by N sub S. So this is a good equation, but it's not quite the way we normally write it. You can see in this equation, we got the primary values on the left side and the secondary values on the right side. What I'm going to do is solve so that I get both of the voltage values on the left side and the number of turns on the right. So what I'm going to do here is I'm going to divide both sides by V sub S. All right, so I'm going to get V sub S in the denominator down here. and it's going to cancel out from over here. And I'm going to multiply both sides times n sub p. All right, so I'm going to divide both sides by v sub s. So that gets me v sub p divided by v sub s. And then I'm going to multiply both sides times n sub p. So that gives me n sub p over here, and it cancels out over here. So I have n sub p divided by n sub s. All right, this is the first of the very common transformer equations. All right, this is one of two that I'm going to give you today. Right, so this is one of the important transformer equations. Also, I want to point out that this value right here, n sub p divided by n sub s. There's a term for this, n sub p divided by n sub s. The number of turns in the primary divided by the number of turns in the secondary. This is called the turns ratio. Right, this is the turns ratio of the transformer. It has no units because the units up here would be turns and the units down here would be turns, so it just cancels out. So it's a unitless, dimensionless number. It's just a ratio between the number of turns in the primary and the number of turns in the secondary. The other important thing that we can recognize, and it's a bit of an assumption, but it's a pretty decent assumption, we can make the assumption that the power that we apply to the transformer through the primary windings is equal to the power we're going to get out of the transformer via the secondary windings. In other words, we can say that power is conserved. In other words, we can say that this transformer is 100% efficient, which of course is an assumption, but it's not a terrible assumption. Most transformers are on the order of 97, 98, or 99% efficient in terms of the output power divided by the input power. So it's a decent assumption. So if we say that the power in via the primary windings is equal to the power out via the secondary windings, we can further say that the power in is equal to the current through the primary windings times the voltage across the primary windings. That's power in. That's equal to the power out, which is the current through the secondary windings times the voltage across the secondary windings. All right, and what I can do is do a little bit of algebra on this. I want to divide both sides by v sub s. Okay, so I'm going to divide both sides by v sub s, and then I'm going to divide both sides by I sub p. All right, so that's what I'm going to do. I'm going to take both sides divided by v sub s. That gets me v sub p divided by v sub s. Okay, and then, like I said, I'm going to divide both sides by I sub p. So that gives me I sub s divided by I sub p. All right, and that's the secondary one. That's the second transformer equation that's important to know. All right, let me go ahead and rewrite this one final time. Those are all the equations, but let me write it again in a more concise manner. So if you look at this, I'll make you be able to see both of these. All right, so here we have an equation. The ratio of primary voltage to secondary voltage is equal to the turns ratio, primary turns divided by secondary turns. Here, we have that same term on the left-hand side. We have V sub P divided by V sub S. V sub P divided by V sub S equals the current in the secondary divided by the current in the primary. All right? This is a big thing to point out right here. In all of these terms, I have primary divided by secondary, primary divided by secondary, primary divided by secondary, except for this current ratio right here. The current ratio is the secondary current divided by the primary current. So I'm going to rewrite this one last time by recognizing that this equals this, and this is the same thing as we have down here, and it equals this. So in reality, this term and this term and this term are all equal to each other. So let's go ahead and write that one last time. Nothing really new here, just rewriting it. So V sub P divided by V sub S equals N sub P divided by n sub s. That's this equation right here. And then I can also say, well, this is the same thing as this is, so I can set that equal to I sub s divided by I sub p. All right, so this is really, if you're only going to remember one thing about transformers, this is the thing to remember. That's the equation to remember. So now I can solve for any of these terms. If I know the voltages and I know one of the turns, say in the primary winding, I can solve for the turn in the secondary winding. Or I can solve for any one of these various different things just by knowing three other things. One more thing I want to point out here, would this work for DC voltage? What if I applied, 24 volts DC to the primary windings? Would I get a DC voltage out? The answer is no. And the reason why it's no has to do with the changing magnetic field. If I apply a DC voltage right here, I will get a magnetic field around here. But will that magnetic field be changing? No, it will not be a changing magnetic field. And if we don't have a changing magnetic field, then we don't meet the requirements for generator action over here for the secondary windings. Specifically, this value right here would be 0 if I didn't have a changing magnetic field. And so if this value for the changing magnetic field is 0, then it doesn't matter how many turns I have in the secondary, my voltage in the secondary would be 0. So a transformer only works with AC voltage, which is actually the second reason. If you think back a few class sessions, I said there would be 2 reasons why AC voltage is more convenient for the electric grid. One, we already talked about. One, we said that, well, AC voltage is just what AC generators naturally produce. In fact, all generators. It's what all generators naturally produce if they have a rotating something inside of a stator. All right, so they're naturally producing AC voltage anyway. If you want to produce DC voltage, you got to do things like add a split ring commutator, add coils to the armature. You have to do some extra stuff to make it DC. So it's more convenient to use AC electricity on the electric grid because it's what generators naturally produce in the first place. And the second reason is because we can use transformers. And transformers allow us to step up the voltage to put it on a transmission line and make the transmission of the electrical energy much more efficient. And then at the other end, step down the voltage from the electric grid to household voltage. And that way you can have a lower voltage inside your house. All right, so the input is always the primary. Your power is coming in on the primary side, and your output is the secondary side. So if you want a higher voltage on the secondary than you have on the primary, this is called a step-up transformer. If you want a higher voltage on the secondary than you have on the primary, then you want this value, this ratio, to be much less than 1, right? So if you want that to be less than 1, it's equal to this, so you want the turns ratio to be much less than 1. All right, so you need a lot more turns on the secondary winding than you do on the primary winding. Conversely, at the other end of the transmission line, if you want the secondary voltage to be much lower than the primary voltage, then look down here. You want your secondary voltage to be lower than the primary voltage, so you want this value to be much greater than 1. Therefore, you want this value to be much greater than 1. Therefore, you want more turns on the primary winding than you have on the secondary winding. I'm going to do something kind of unconventional now. I'm going to give you the answers to the next lab. And the reason I'm going to give you the answers to lab 14 is because lab 14, transformers, is going to be material that will be on exam 2. So you will see transformer questions on exam 2. However, lab 14 is not due until after the exam. Why do I do that? Because I want you to make sure you're focusing on studying for the exam. Don't stress out about finishing lab 14. That being said, it would be a good idea for you to do lab 14. I just don't want you to stress out about it too much, so I don't make it due until after the exam. So to make all of that kind of work, I'm going to give you the answers to lab 14. The deal is when you do turn in lab 14, when you submit it, if all you have written down are the answers that I'm about to give you, then you're not going to receive credit for doing lab 14. So you have to show your work, especially now that I'm giving you the answers. So that's the deal that I'm going to give you. I'm going to assume that you are amenable to this deal. I think it's a good deal for you. So here are the answers to lab 14. Number 1 on lab 14, page 97, the answer is 24 volts AC. Number 2, the answer is 0.4 amps. Number 3, the answer is 46.7. It's just asking for a turns ratio, so there is no unit on number 3. Number 4, we had the same transformer as in number 3. What's the current? The answer is 56 amps, 56 amps. And number 5, I want to talk just a little bit in more detail about this one. It's a little bit different looking transformer. It doesn't just have a primary winding and a single secondary winding. You can see that what it's done in figure 2 on page 98, it actually divides up the secondary winding into 2 halves. All right, so when it tells you in number 5, it has a turns ratio of 10 to 1, that means for all the primary windings compared to all the secondary windings, it's 10 to 1. There are 10 times more primary windings as secondary windings. However, of those secondary windings, that's further divided into 2, and half of those secondary windings are being used in the top half of the transformer, which is what's going to be used to create V1, and the lower half of those secondary windings are going to be used to create V2, the bottom half of the secondary windings. And then V3 uses all of them. So when you're calculating V3, the turns ratio is 10 to 1. When you're calculating V1, well, you have half as many secondary windings as you had when you were calculating V3, all right? So I'll give you the answers. The answer to V1 and V2 are both 120 volts, and the answer to V3 is 240 volts. There are a couple reasons why I give you this problem, number 5. First of all, this is a very realistic problem. In fact, most of you have transformers like this in, well, outside your home. Normally they're in those green boxes, those utility boxes out in your backyard or sometimes your front yard. Or if they're not there, if you have overhead transmission lines, they're in a bucket. It's actually called a bucket transformer. And that's exactly what this does. It transforms the primary voltage into 2 secondary voltages. You have the half voltage on top, which is V1, the half voltage on the bottom, which is V2, and you have the full voltage, which is twice as much. It's 240 volts, which is V3. This is called a center tap transformer, because you're taking a tap not just on the ends of the secondary windings, but also at the center of those secondary windings. And how you use this in your home is that about half of your appliances in your home will be connected to use V1. The other half will be connected to use V2. And there are a few appliances in your home, like your air conditioning system, if you have air conditioning, and your stove or oven, most likely, and your dryer, if you have an electric clothes dryer. Those 3 loads, in most cases, will use the full 240 volts because they're very large appliances. It's convenient to design them to use a higher input voltage. So if you have a really large load in your home, you can use the full 240 volts V3. Otherwise, for most of your standard appliances, you just use a wall outlet, which is 120 volts. I don't know if you've ever plugged in an electric clothes dryer before, but the plug does not look like a standard wall outlet plug. And the reason for that is because they don't want you to be able to plug that clothes dryer into 120 volts. It's not designed for that. It's designed for 240 volts AC input. So they have a different plug, and the only way you can plug it in is to plug it into a 240 volt outlet. All right, so those are all the answers for Lab 14. Make sure you understand how to do them, show all of your work to do them. But now that we've gone through this, there's only a couple of equations that are relevant. I've given you the answers, so I think you can probably figure it out. All right, so that's the end of this video. In the next video, we're going to talk more about what's going to be on the next exam. I'll see you there.